Welcome. In this session on natural deduction, we'll explore some of the properties that predicate logic has. Let's suppose that we're in a metalogic. And this metalogic, for example, could be Zermelo-Fraenkel set theory. And we have a set of premises, and these are gamma, and each one is a formula, and we have a conclusion, and we'll just call that a formula C. One of the early questions that was asked in natural deduction was, for propositional logic, is every valid argument a semantic entailment? And we can extend that to predicate logic. And so this would be a question of what is called soundness, and sometimes it's called correctness. We'll use the term soundness. And soundness is a statement in our metalogic, and that is that if we can use the rules of natural deduction to go from our premises to our conclusion, then we can conclude that the premises semantically entail the conclusion. And this is something that we think had better be true, or we've been doing a lot of work in natural deduction that is out the window. So this kind of result was proved fairly early in the history of logic. And we can just outline the method as being, I'll call it structural induction, which is a common term for it. Structural induction, and that is on the length of the proof of gamma, therefore C. That is, if you have a proof for it, then that proof has a finite number of lines. And so we can use induction on the number of lines to show that if it's a legitimate proof, then semantic entailment has to hold. And essentially, that begins with, if the proof has one line, then that means the premise and the conclusion are the same, and so it holds. And if the proof has k plus 1 lines, and we know that this works for k, then we say, well, that conclusion can only be arrived at by using one of the rules of natural deduction. And so we can enumerate the number of rules of natural deduction and go through each one of them and show that if it was a legitimate way of arriving at the conclusion from the premises, then that was also a semantic entailment. The converse of this if-then statement took quite a while and required a very clever proof. And this is called completeness. And completeness is, this was shown in the PhD thesis of a famous logician, mathematician, thinker, Kurt Gödel. And that was in 1929. And I haven't read his thesis in German because I don't read German. I have read translations of this and gone through his proof style. And this is the statement that if a set of premises semantically entails a conclusion, then there is a finite length proof in natural deduction from the premises to the conclusion. And this method, I will simply say, is highly technical. That is, it is indeed a suitable topic for a PhD thesis. And Gödel originally proved this using what's called a Hilbert axiomatic system, and it was later demonstrated that this is also true in natural deduction. So we can summarize this as a syntactic statement and a semantic statement, and we're both making each of these statements in our meta logic. We can say that a set of premises can be used to prove a formula if and only if that is also a semantic entailment. This is sometimes referred to as the first theorem of completeness, or simple completeness. There's an additional one that can be made, and its proof technique is often quite different, and you can demonstrate that if one of these holds, the other holds. And this has to do with refutability. This is a slightly remarkable statement, and that is, we make this also in our meta logic. Either a formula is satisfiable, or we can find a proof of the negation of that formula. And sometimes this property, that there is a proof of the negation of a formula, is called the formula is refutable. That is, you can prove the negation of it. And this statement is a semantic statement. That is, it's about satisfiability and about the existence of a model for a formula. This is a syntactic statement, and it's talking about the existence of a finite length proof within the rules of natural deduction. And one of the completeness results is that either a formula is satisfiable, which is a semantic statement, or a formula is refutable, which is a syntactic statement. Taken together, what these mean are that because of soundness and completeness, we can rely on the results of the predicate logic for natural deduction.